Okay, we have a real new classroom. How is it? Better than the other one, right? I set the temperature about 60 this morning and somebody raised it up. So it's about 70 something. So I put it on 65 again. So, hopefully, usually 70. Yeah, about the same. Yeah, but look at the number of students here. It's like, the one, about this size, when you go to house, right? Yeah, it's hot and humid. Here. Yeah, we need to have, the 2 sections of this class. So we can have about, the 10 or so. 25, too many. But this one is better than, like the class that I taught about 10 years ago when I was in Texas. It has about the same room size, and there were 65 or 70 students. About not exactly the same. It was a heat transfer course, and there were only about 40 chairs, so 20 of them was standing in the back. Yeah. Huh? On their foot. So if you don't come, the bands, there's no chair, there's no seat. Yeah. So this one is more like, more for humanity. There is more like a factory, manufacturing facility, manufacturing engineers. Here we train engineers, they manufacture. Okay, we are going to talk about ideal gas equation. Last Tuesday, we learned how to. So you're okay with this classroom? We still have an option to go back. We reserve both of them. So later, if you want to move them, we can do that. No, this one is better, right? There are only two instructors using this classroom, me and Dr. Drew Wilson. So I'm the only one in this classroom, Tuesday, Thursday. He's using this one, Monday, Wednesday. Isn't it nice? No? So last Tuesday, we studied how to evaluate a property of a phase change material. So we had to use property diagrams such as pressure diagram or temperature diagram to determine the phase change process of our system. And then we had to go to appropriate, the table to evaluate their properties. If the pressures or temperatures are not available directly, we have to use a linear interpolation to get our value, right? But when we have a pure system that never undergo phase change during our, the process, then we can use much simpler equations such as ideal gas equation, and later we are going to talk about specific heat equation, okay? So we are going to talk about both of them to see, how we can evaluate their properties. The first one is ideal gas equation, which is pretty simple. As simple as this one. PV is RT. PV is RT. By the way, you all know that when you see this lowercase means it's actual property, actual volume divided by mass, and then you have a lowercase to distinguish between specific volume and actual volume. By the way, specific property is the property divided by mass, okay? So we can also rewrite this PVRT by PV is MRT. So that means as long as we know this gas constant R, if you know pressure and temperature, you can determine its a specific volume If you know specific volume and temperature, you can determine pressure. So you don't have to go through a number of tables. You can use this equation to determine unknown property. Okay. Then how can we determine this gas constant R? This gas constant R is a material specific. So there's a gas constant for air, there's a gas constant for oxygen, a gas constant for nitrogen. So each gas has its own gas constant. Then how can we determine that? Of course, we can use a table, but there's another way to determine this gas constant, which is R bar divided by N. This R bar is called universal gas constant. So there's only one universal gas constant. Its value is 8.314 kilojoule per kilomole Kelvin. If you don't remember this number, you will remember this number after this class, because in Thermodynamics 2, we use this one rather than this one. We will talk about that next week. And this M is not a mass, it is molecular weight. Or some people like to say molecular mass, molecular weight, they're the same thing. And what is molecular weight? Molecular weight means that, that the weight, not the weight, the mass of a substance per mole. So if you have 1 mole of a substance, the mass of the system is going to be molecular number. So usually, if you go to the first table, by the way, you are all familiar with this table that we used it many times in EGR456. And this one is molecular weight. So you can see the unit, kilogram per kilomole. So when you have 1 kilomole of your system, how much, the weight is it? That is molecular weight. So for example, if you have oxygen here, molecular weight is 32 kilogram per kilomole. So for example, molecular weight of oxygen is going to be 32 kilogram per kilomole. Then you must be pretty, familiar with this kilogram, but maybe not for kilomole. Kilomole means 1 mole is 6.023 times 10 to 26. So if you have that many oxygen molecules, then the weight of the mass of the system is going to be 32 kilograms. Okay. So that is molecular weight. So if you use this molecular weight, and you can determine the gas constant. So here we have 32 kilogram per kilomole. Then you get gas constant R of oxygen. Okay. What is it? Calculator. 8.314 divided by 32. So we have 0.26, approximately 0.26 kilojoule. Kilomole will be cancelled. So we have kilojoule per kilogram Kelvin. Kilojoule per kilogram Kelvin. So that is gas constant. Then what is the unit? This one. So if we use this ideal gas equation for oxygen, it's going to be pressure times specific volume is gas constant of oxygen times temperature. In this case, the unit of this gas constant is kilojoule per kilogram Kelvin. Temperature should be in Kelvin, and specific volume is cubic meters per kilogram, and pressure is going to be Pascal. Kilopascal, because we have kilo here, right? So that's how you can use this ideal gas equation of a state. When you go to the thermodynamics 2, we are going to study this gas ideal gas equation on a molar basis. This one is mass basis. So you see this kilogram here. If you go to molar basis, this equation is going to look like PV nRT. So in that case, everything is the same, but this N is number of mole, and this R is going to be this universal gas constant. But we will talk about this one later next week when we study thermodynamics 2. Okay. So let's go back to this thermo 1. PV is RT. So where can we use this equation? If you look at this equation, this R is a gas constant. It has a fixed number, so this R is constant. But this pressure of oxygen can be any number. If the pressure of oxygen in this classroom is going to be about 100 kilopascal, but if you talk about the oxygen tank in one of the laboratories over there, their pressure value is going to be much higher than 100 kilopascal. So this pressure can be any number, 200, 350, any number. So this one is a variable. What about this specific volume? This specific volume can be also, the many numbers. For example, if we look at any property table, specific volume, this V can be 200, 155, 147, depending on pressure and temperature. So specific volume V can be also any number, variable. Temperature can be any number. Here now about 20 degrees Celsius. If we keep running the air conditioning, temperature goes down. If I turn it off, temperature goes up. So the temperature of the air in this classroom can be any number, right? So this one is also a variable. However, the gas constant of oxygen should be always this number, no matter what, how the high the pressure is or how high the temperature is. So this one is the only constant in this equation. This one is variable. Then why don't we move this temperature to the left-hand side? Then we have PV over T is gas constant R. Then this one is constant. This one is variable. This one is variable. This one is variable. However, the whole thing should be constant. So if you write this gas, the ideal gas equation in this form, pressure times volume divided by temperature should be always constant. So as long as you have the same oxygen, PV over R should be always this gas constant. Okay? So pressure times specific volume divided by temperature at the initial state, T1 V1 over T1 should be the same as P2 V2 over T2. Then let's say, if I want to, if I want to increase the pressure of the oxygen in this classroom without changing the temperature by the, the air conditioning unit, then what happened to its volume? You don't have to look up any table. If you maintain the temperature, T1 is the same as T2. T1 is the same as T2, so we can cross them out. And if you increase pressure twice, so this one is going to be 2 times P1. So P1 will be cancelled. You can see V1 is 2 times V2. So you can calculate the relation between the initial state and the final state by using this equation. That's how we use ideal gas equation. Okay. So that's one of the equations that we are going to use when you have a pure system. There's another one, which is a specific heat. So when we studied the steam table to determine a property of phase change material, what are the properties that we usually interested in? Specific volume V, specific internal energy U, and specific enthalpy H. So V, U, and H, those are the, one of the, the common properties that we want to determine. So they are specific volume V, specific internal energy U, specific enthalpy H. So if you are interested in this specific volume, we can use this ideal gas equation, right? Then what kind of equation we can use to determine U and H? They are specific heat. So for this one, we can use PVRT or P1V1 over T1 is P2V2 over T2. They are ideal gas equation. If you want to determine U and H, we can use a specific heat. There are two specific heat. One is CP, the other one is CV. The equation we are going to use is simple. Delta U is CV delta T. The other one is delta U, H is CP delta T. What is delta means? Difference. Difference in U. Difference in U between number one, the initial state, and number two, the final state. So how do you determine the difference in internal energy between the initial state and the final state? Let's assume that you go to, the one of the buffet, dining hall, and have, the heavy, the lunch. How are we going to determine the difference in your weight? You can measure your weight before you enter the buffet, and then you can measure the weight, after eating a lot of, the lunch. Then you can calculate the difference. The weight after having lunch minus the weight before having lunch. So you can calculate internal energy U after a process minus internal energy U before a process. U2 minus U1 is how you determine the difference in U. Is CV, specific heat, times difference in temperature between the initial state and the final state, so which is the same as this way, T2 minus T1. So this is how we determine the change in specific internal energy U. Similarly, now you get the idea how to determine delta H. H2 minus H1 is CP T2 minus T1. So these are the equations you can use to evaluate a property of pure materials that doesn't undergo phase change. Okay. So that's all the theory that we need. Let's solve some practice problems. But before, going to, solve some practice problems, we need to review the energy balance equation we are going to use to solve a thermodynamics problem. So how can we determine what are the energy balance equations that we studied in Thermodynamics 1? There are two of them. One is for a closed system. The other one is for an open system. So closed system, and the other one is open system. What is the difference between a closed system and an open system? Mass change. If there's a mass change during a process, it's a closed system. If there is no mass change in the system during the process, that's a closed system. If there is a mass transfer, such as inlet, exit, then it is an open system. So there's a mass change, delta mass, there's no of them. Delta M, yes, for an open system. And we usually, when we study open system, most of the open systems in engineering, they are steady open system. And most of the closed system are going to be unsteady or closed system. Do you know the difference between steady and unsteady? Steady means time independent. Unsteady means time dependent. How do you know whether it is steady or unsteady? You can look at a property of your system. If the property changes in time, that's a time dependent unsteady system. If the property does not change in time, that's a steady system. If I want to study the heat transfer from this hot coffee to the surroundings, what is the main property that you are interested in? The temperature of this coffee. So does it change in time? Currently hot, an hour later it's still hot? No, the temperature goes down in time. So that's an unsteady process. What about this cell phone? So an hour later it becomes like very hot and fireball? No. An hour later it becomes an ice? No, it's a steady process. Make sense? Okay. So we have two equations, one for unsteady closed system, the other one is open steady system. So since you already studied these energy balance equations, so I'm not going to explain. I will just write them down. If you have a question, you can let me know. You can interrupt anytime. So unsteady open closed system, the energy balance equation is Q in plus W in minus Q out. W out is mass times U2 minus U1 plus moving boundary work. We are going to talk about moving boundary work in the next slides, so don't worry about that. This one is moving boundary work. That's on a closed system. And sometimes we can simplify the right-hand side of this equation. If you have a constant volume process, then there is no moving boundary work. Moving boundary work means if you talk about this cup, there's no moving boundary. Moving boundary work means that it expands or it compresses. So when you see a volumetric change, then you have a moving boundary work. When there is no volumetric change, then there is no moving boundary work. So if you have a constant volume process where there is no moving boundary, then the equation on the right-hand side is going to be M U2 minus U1. This is constant volume process. Or if you have a constant pressure process. What is constant pressure process? Pressure does not change during a process. What is a constant pressure process? Our life. We are experiencing atmospheric pressure. Does it change? Slightly, depending on, when there's a rain, during the climate, but it usually, we can assume that practically constant, approximately 100 kilopascal, unless you go on top of Mountain Everest or you live underground like mermaid or something. So our life is going to be constant pressure process as long as we breathe, right? Because the atmospheric pressure is almost constant. So in that case, we can use mass times H2 minus H1. That is constant pressure process only. So we have three options on the right-hand side. So that is the energy balance equation for an unsteady closed system that you studied in chapter 3 of Thermodynamics 4. Or you have a Thermodynamics 4, you can go to chapter 3. So this is the only equation that you're going to use. We have, the several problems that we will solve together in the classroom. So don't worry about that for now. What about steady open system? The energy balance equation is going to be Q dot in plus W dot in plus M dot at the inlet. This one has inlet, I'm going to say number 1, enthalpy, kinetic energy, potential energy is going to be Q dot out. The heat transfer rate comes out of a system. Energy transfer by work comes out of the system per unit time plus M dot, if we say exit is number 2. This one has H2 plus kinetic energy at the exit plus potential energy at the exit. So this one is energy balance equation in an open system. You see this dot. This dot means that property divided by time. So if we have a property, let's say this Q, if you divide by mass, it becomes specific property, right? If you divide by mass, Q divided by mass, you get lowercase q. If you divide by time, it becomes Q dot. Q dot is not heat transfer. Q dot is going to be heat transfer per unit time. So it is the rate of heat transfer. Or if you divide Q by mass as well as time, then you get Q lowercase q dot. The rate of heat transfer per unit mass. Okay. And when you have a steady open system, it is convenient to use rate form rather than the general energy balance equation. So we divide each term by time, and then we put that on top of it to show that we divided each term by time. So these are the equations that you can use in thermodynamics for energy and enthalpy. For entropy, we are going to talk about that later today. Any question up to here? So that's a summary about energy balance equation, how to evaluate a property. No question? Too easy, right? We already studied thermodynamics 1, and we already found that how easy that is. So if you are disappointed with thermo 1, then you won't be disappointed for thermodynamics 2. It's going to be challenging. Okay, based on that, let's solve some practice problems. Let's go with the easiest one first. I think this equation is the easiest in anywhere in engineering, right? The ideal gas equation. No? A rigid tank contains an ideal gas. Oh, by the way, do you remember what is an ideal gas? As a definition, the definition of ideal gas is a gas molecules which can move without any interaction with the nearby particles. So it can randomly move. So there's no restriction, there's no pressure, and etc. So usually real gas can behave like an ideal gas when pressure is low or temperature is high, which means that when density of the system is low. Density of the system is low. Low density means there's a less particles out there, so you can more, freely move, right? So usually when pressure goes down, temperature goes up, the gas behaves more like ideal gas. So that means if you have a high pressure or low temperature, you cannot use ideal gas equation. Okay? So let's solve this problem. There's a rigid tank. Rigid tank means volume is constant. That's a rigid tank. It contains an ideal gas at 1227 degrees Celsius. So initially, 1227 degrees Celsius and 200 kilopascal, and the gas cooled until the gas pressure reached 50 kilopascal. So finally, it becomes 50 kilopascal. And if the atmospheric pressure is 100 kilopascal, PATM is 100 kilopascal. And we want to determine the final temperature of the system. So we want to determine the final temperature. So it's it's an ideal gas that doesn't undergo phase change. Then you have two options, ideal gas equation and specific heat. So why don't we use this ideal gas equation? We see this one, P1 V1 over T1 is P2 V2 over T2. So let me write that equation here. P1 V1 over T1 is P2 V2 over T2. So specific volume V1 and specific volume V2. What is the relation between V1 and V2? They are the same, right? Because you have a rigid tank, the volume does not change. It is closed, so mass does not change. So when you have the same volume, same mass, your specific volume does not change. So V1 is the same as V2. If you have the same V1, V2, you can cross them out, right? So I'm going to get rid of them. So it's going to be P1 over T1 is P2 over T2. So what is P1? 200. What is P2? 50. What is T1? 1227. What is T2? This one divided by 4. So if I calculate 1227 divided by 4 and 306.75, 306.75 degrees Celsius. Is this correct or not? No. Why? What is the problem? Kelvin, right? You cannot use degrees Celsius when you use this ideal gas equation. You have to use Kelvin. So instead of 1227, you have to use plus 273. It's going to be 1500. So it's going to be 1500. So if you solve this one, 1500 divided by 4, 375. So if I write, not this one, you're wrong, 375 Kelvin. Now we are good? Good? No. What's the problem? Right, it's a gauge pressure. So you cannot use gauge pressure. You have to use absolute pressure. What is the relation between absolute pressure and gauge pressure? Gauge pressure is the difference between absolute pressure and atmospheric pressure. So to determine absolute pressure, you need to calculate 200 kilopascal plus 100 kilopascal. So absolute pressure inside this rigid tank is going to be 300 kilopascal. So this one is not correct. It's going to be 300. And what about the final state? 50 plus 100, so 150. So if you solve it, you get 750 Kelvin. Okay? Any question? And you may have a question, like this one. If we are going to use absolute pressure. Why do we need to study gauge pressure? Is there any, the equation that you use only gauge pressure? You already studied fluid mechanics, fluid statics and fluid kinetics. That we use gauge pressure rather than absolute pressure. You remember that? I didn't teach that course. I'm not responsible. No. So as long as that you have a atmospheric pressure applied to everywhere, you can cancel that out. You can only use the gauge pressure to calculate the flow movement, right? We can talk about that later, when we go to heat transfer, because there's many similarities between fluid mechanics and heat transfer. Okay. So the next problem, we're going in the amount of 0.6 kilogram filled 0.05 cubic meters piston cylinder device. Piston cylinder device. There's nothing new. The piston cylinder device means any system whose volume can change. So we use piston cylinder device a lot because that this piston can move up and down. That will change the volume of the system. Okay? So when you have something like that, if the mass is 0.6 kilogram, its volume is, initial volume is 0.05 cubic meters, and pressure, when it doesn't say whether it is gauge pressure or absolute pressure, you can just assume that it is absolute pressure, okay? When its pressure, P1 is 550 kilopascal. Now the piston is now moved by, change the weight. I don't know how, that you can change the weight, but until the volume is twice its original size. So there's an expansion process. Volume is now this one multiplied by 2, 0.1 cubic meters. During this process, the temperature is maintained constant, determine the final pressure in the device. So T1 is the same as T2. We don't know T1 is what is T1, what is T2, but we know they're the same. And you can use the same energy, the same ideal gas equation, which is this one. T1 V1 over T1, P2 V2 over T2. P1 V1 over T1 is P2 V2 over T2. So T1 is the same as T2. So you can cross them out. So we only have T1 V1, T2 V2. T1 is 550. V1 is 0.05 divided by 0.6. T2 is, I don't know, V1 is 0.1 divided by 0.6. So you can cross 0.6, 0.6, 550 times 0.05 divided by 0.1, you get 275 kilopascal. So that's how you determine the final pressure. Any question? Is it too fast or too slow or good? Really fast. I will slow down. I'm not going to talk about compressibility chart that we don't need in Thermo 2. Moving boundary work, no, we don't need in Thermo 2. Let's talk about energy balance equations. Okay, this one. Now, based on the energy balance equation that we reviewed, which is shown here. So let's solve this problem. So it's a closed system. So we are going to use that energy balance equation. Okay. We have a refrigerant R134 at 600 kilopascal and 150 degrees Celsius. So we have information about the initial state. So we have information about the initial state. So in a spring-loaded piston cylinder device, spring-loaded piston cylinder device means we have this cylinder, we have this piston, and there's a spring. And there's a R134A. It's a gas inside. So which one is our system? Spring, piston, cylinder? No. This is our system, right? What about, is it the surrounding? No, the surrounding is going to be outside. So we want to determine heat transfer, energy transfer between our system and the surroundings. Okay, that is how we design a thermodynamics problem. So initially, T1, initial pressure is 600 kilopascal. Initial temperature T1 is 150 degrees Celsius. And initial volume V1 is 0.3 cubic meters. And now we have a cooling process. Cooling process means heat is removed. So there's a Q out from R134A. So now we have the final temperature, minus 32 degrees Celsius. And its volume, V2, is 0.1 cubic meters. Determine the heat transferred, which is this one, and the work produced by the refrigerant during this process. So let's write down the energy balance equation. This is not going to be constant volume process or constant pressure process, because pressure, we have no idea what's going to be pressure later, and volume is not constant. So none of them. So we have to use the main equation. So let me write the main equation here. Okay. So the main equation is going to be Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work. The work associated with moving boundary. Then let's see, are we going to use all of them? No. First of all, we know it's a cooling process. So we have this one. Then, do you have Q in? When you have Q out, that means heat is transferred from the system to the surroundings. What is the second law of thermodynamics? The second law of thermodynamics is heat is transferred from high temperature point to a lower temperature point. So when heat is removed from this R134A, that means R134A is at higher temperature than the surroundings, right? So is there heat transfer goes in when it is at higher temperature than the surroundings? No. So we can neglect Q in. What about work? What kind of work is there? We can definitely see this spring. So there's a spring work. What this spring work does, it changes the volume, right? What is the work that changes the volume among these three? Yes, boundary work. Because this is the work that will change the volume, right? So the spring work is going to be this one. So we have this. What about W in, W out? Is there any information related to W in or W out? No, so you can neglect them. And is R134A is a pure system, pure material, or phase change material? So there are two materials, that we use as a phase change materials. They are water and refrigerant. This one is a refrigerant. So it's going to be so someone is controlling this classroom, right? The dark power. No? Okay. So I'm just trying to wake you up because we just had a lunch. I know that, it depends on the MSG level in your food. Sometimes you get, right? No? So it's a phase change material. So we have to evaluate U1 and U2 independently by using property table, determine its phase, and then go to a proper table, okay? What about the mass? Oh, we also need to evaluate the mass because mass is not given. So to solve this problem, we should be able to determine this mass, we should be able to determine this specific internal energy and WB. Then we will be able to determine Q out. And that's the end of the story. So let's do that. First of all, M. How do we determine the mass of the system? Last week, we studied if you know two property values, you can calculate, you can determine another value, right? And if you know pressure and temperature, you remember the table problem, right? If you know pressure and temperature, you can evaluate H, U, V, etc. So if you know pressure and temperature, you can evaluate V, specific volume. That is different from this volume. This is the actual volume. Specific volume is actual volume divided by mass. So if you know the specific volume, then you can calculate the mass, right? So if you calculate specific volume V, which is actual volume V1 divided by mass, and we already know V1, if you know lowercase v1, you can find mass. So that's our plan. So let's do that. To do so, we need a table. So let's find this V1. How can we do that? Can we just go to a random table and find V? No, you can't. You need to determine the phase change process first. How do we determine the phase change process? By using a phase diagram. So what kind of diagram that we are going to use? Since we know pressure and temperature, you can make temperature diagram using this pressure, or you can make pressure diagram using this temperature. So what table do we have? We have a pressure table. So why don't we use this pressure to make temperature diagram and use this temperature to determine its phase, okay? So I'm going to use this 600 kilopascal here. At 600 kilopascal, we can make T something diagram, but we are interested in this specific volume. So why don't we make TV diagram? So let's make TV diagram, which looks like this. So to complete this TV diagram, we need to know three property values. They are T set and VF, VG. So how can we find T set, VF, VG? From 600 kilopascal. So let's go find 600 kilopascal. Where is it? The pressure is in bar, so 600 kilopascal is 6 bar, so this is the pressure. So at 6 bar, this is the temperature. He said is 21.58. 21.58. That is the saturation temperature. Then, what is the temperature of our system? 150. So, 150 is much, much greater than 21.58, somewhere up here, right? So, where is our system? Right here. So somewhere here is going to be 150, pretty high. So this is our system. Now, what is the phase change process at this location? 1, 2, 3, 4, 5. Here is 1 compressed liquid. Here, this point is saturated liquid, saturated mixture, saturated vapor, and superheated vapor. So we have superheated vapor in our system. Throughout this cooling process, now we only have superheated vapor at the initial state. We have no idea about the final state. So you have to re-evaluate the phase change process at the end of this cooling process. Okay. So here we have phase change process number 5, superheat vapor. So if you know it is a superheat vapor, how you evaluate its property? By going to superheat vapor table. Where is superheat vapor table? The superheat vapor table is right here. Table A12. Table A12, superheat vapor table, when pressure is 0.6 megapascal. 1 megapascal is 1000 kilopascal, so 0.6 megapascal is 600 kilopascal. So that's our pressure. What about temperature? 150 degrees Celsius. So the temperature is the first column. Where is 150? Right here. So what do we want to determine? V, U, H, S? No, we want to determine V. So at 150 kilopascal, I'm sorry, 150 degrees Celsius at 600 kilopascal, V1 is going to be this number, 0.0555. So I'm going to write this number here, 0.0555. Then what is the volume? V1, 0.3 cubic meters. So this one, 0.3 cubic meters. So we have a V1, capital 1, capital V, and lowercase v. Can you determine the mass? Yes, we can. If you do, the mass is going to be, where are you? 5.41. So approximately, this one is 5.4 kilogram. So that goes here, 5.4 kilogram. But that's not the end of the story. We also need U1. So where is U in our system? Right here. So the value we are looking for, this U, is going to be this one, 359.21. So at the initial state, U is going to be this number, 359.21. So I'm going to write this one here. 359.21 kilojoule per kilogram. Okay, now it's time to determine U2. So what information do we have to determine U2? I guess, I think we have temperature. Since we already determined the mass, 5.4, and we have V2, so at the final state, we have T2, which is minus 32 degrees Celsius. We have lowercase v2, which is capital V2 divided by mass, which is, capital V2 is 0.1, mass is 5.4, so V2 is 0.0185. 0.0185 cubic meters per kilogram. So we have temperature and specific volume. Can you determine the phase change process? Yes. Oh, wait, we already have two property values. Can you just determine the phase change process here? No, you can't, because you need two intensive properties. That capital V is an extensive property, so you cannot use that capital V. You can use specific V. Okay. So we have a minus 32 degrees Celsius, 0.0185. So let's find U2. How can you determine U2? We go to a random table? No. You need to determine its phase change process. How can you determine its phase change process? By using another phase diagram, another property diagram. So what kind of property diagram we are going to use? TV again? Unfortunately, if you want to make TV diagram, you need to know pressure. But we have no pressure information at the final state. We only know temperature. So instead of TV, we can make TV diagram at minus 32 degrees Celsius. So at the final state, we can make PV diagram at minus 32 degrees Celsius. This graph looks like this. Okay, so if you want to complete this PV diagram, we need to know three reference properties. So they are P set, VF, VG. So where can we determine this P set, VF, VG? From this table. So we have minus 32 degrees Celsius. T sat is going to be 0.7704. However, the unit of this pressure is bar. So you want to convert this one into kilopascal. By how? By multiplying by 100. So the pressure P sat is this one, 77.04 kilopascal. What about VF and VG? So VF is here, VG is here. So VF is 0.7172. So if you write 0.7172, is that right? No, VF is this value divided by 1,000. Because VF is usually very small, so we multiplied it by 1,000 and wrote it here. So if you want to determine VF, you need to divide by 1,000. So this one divided by 1,000, which is times 10 to minus 3, that is VF. What about VG? 0.2451. 0.2451 cubic meters per kilogram. So now we just made this PV diagram. What is the specific volume do we have? 0.0185. Let's find that specific volume on this PV diagram. That value is greater than this one VF, but less than VG. So somewhere in the middle. So where is our system? Somewhere in the middle. Right here. So what is the phase change process at this location? 1, 2, 3, 4, 5. So we have number 3, saturated mixture. If you have a saturated mixture, you cannot find its property right away. There is another parameter that you need to determine. Quality X. Because it's a mixture. You have a liquid and vapor together. There are so many different mixtures. You can mix 10% liquid, 90% vapor, 50% liquid, 50% vapor. So depending on the ratio between liquid and vapor, you have a whole different, the property values. So you need to know what is the, the percentage of liquid and vapor in the system. So how can you determine that? By using linear interpolation equation. So we can use the linear interpolation equation for V, U, and H. So which one? Since we have no idea about U and H, so the only option is we use V. So the linear interpolation equation for V is VF plus quality X times VG minus VF. So in this equation, we already know V 0.0185. 0.0185, and VF is right here, 0.7172 times 10 to minus 3. X is unknown, and VG is right here, 0.2451. VF is here again, 0.7172 times 10 to minus 3. So we have everything but X. Can you determine X? No. Yes. So if you do, X is, where are you? 0.0727 6766 cubic meters. I'm sorry, that's a quality X. What is the unit of quality X? No unit, right? It's a ratio between 0 and 1. So about 7% of the mixture is liquid or vapor? Vapor. When it becomes 100%, then it is saturated vapor. If it is 0%, it is a saturated mixture. So the number goes down, it goes close to liquid. Number goes up, it goes close to vapor. Okay. So now we got quality X and everything. So how can you determine U2? Whenever you want to evaluate the property of saturated mixture, always use linear interpolation. But this one is only has V. So we can write another one for U. U2 is UF plus quality X times UG minus UF. So here we know quality X. This one. What about UF? The temperature is minus 32. Minus 32. So where is UF? This one. So the value is 9.47. What about UG? 209.01. So on this line, this one is UF, this one is UG. So 9.47, I'm going to write it here, 9.47. What about UG? 209.01, 209.01, UF, 9.47. So you have everything. Can you determine U2? Yes, you can. So U2 is 23.9898. 23.98, just 99, 23.99. So this one is 23.99 kilojoule per kilogram. So we have almost everything except WB. Wow, I don't like this problem, right? So if you can solve this problem without any difficulty, any doubt, then you're good to go in terms of closed system. So consider that the big giant turtle when you play Super Mario. Isn't that the final boss? Okay, yeah. So don't just think about the breaking the blocks by jumping. Always the final boss is the turtle. So if you can solve this problem without any difficulty, without watching my lecture video, if you can do that, then closed system is done, okay? So now let's find this moving boundary work. If you have a spring-loaded piston cylinder device, how can you determine its moving boundary work? By the definition, moving boundary work can be determined by WB can be determined by 1 to 2 PDV. Another mathematics. So what does it mean? What does it mean? Mathematics, okay, it's the integration, but on a graph, it means it calculates the area when you make volume pressure diagram. So if we have PV diagram, the area is going to can be determined by this integration. Okay. Then how can you complete this PV diagram? Let's talk about this piston. What kind of forces are acting on this piston? Let's think about physics rather than mathematics. If you don't like mathematics, we can only think about physics. So let's not solve this one mathematically. We can talk about physics. So what happens? First, just say anything. Spring. So there's a spring force. You're right. Spring force is, I don't know, it is expanding or compressing, doesn't matter. Because if you just point in one direction, if it is the other direction, the opposite direction, you just get a negative value. If you have a positive value, the same direction. Okay? So that's a spring force. Fs. What else? Yes. You're right, right. Gravity is not a force. So what is the force by gravity? Weight. Right. Yes, weight. So weight, which direction? Downward. So how do you determine weight? Mass times gravity. Mass times gravity. Mass times gravity. How do you know it's a mass times gravity? So Newton's law, force is mass times acceleration. Gravity is an acceleration. So mass times gravity is force. What else? Pressure. So there are two pressures are acting on. Or just one? Yeah, two. If you are not sure, let's assume that there's only one pressure. So there's only one pressure. Pressure by R134A, of course, it is acting on the bottom surface. Is that the only pressure by R134A? Oh, yeah, but I'm talking about the pressure by this R134A. So the pressure by R134A is only acting on the bottom surface of the piston, right? Technically, there's a pressure acting on the side surface, pressure acting on the bottom cylinder. But what happens is that they are fixed. So whether or not they are acting on there doesn't matter, right? Right? Unless the cylinder is weak, then if there's only this pressure, then it will break, right? But these are fixed boundary. This one is moving boundary. So the pressures acting on fixed boundary, we don't care because it doesn't do anything, right? So only the pressure, the changes thing is going to be the pressure acting on the piston. So let's say that is the pressure of our system, just P. Is there any other force acting on? Atmospheric pressure. So if there is no atmospheric pressure, then what's going to happen? What's going to happen? Since there is only pressure by R134A, this piston is going to it will fly out because there's only pressure from the bottom side, right? So if the piston remains stationary, that means that there's a pressure acting on the bottom surface, there's a pressure acting on the top surface, and they are equal. If one is greater than the other, what happens? If the pressure by R134A is greater than the atmospheric pressure, it moves upward until they have a force equilibrium. If the atmospheric pressure is greater than R134A, then piston moves downward until the net force becomes zero, right? So there's an atmospheric pressure acting on top. I'm going to say PATM. So when you do a force analysis, that is what we can do in terms of physics. Now, when you talk about physics, you also talk about mathematics. You need to do both. You cannot just do one, right? So let's talk about mathematics. Then how we talk about this forces in mathematics. We determine a positive direction. You can say downward is a positive direction. You can say upward is positive direction. Doesn't matter. You only see, the change in the sign of each term. So let's assume that I'm going to say upward is a positive. And our assumption is that after this cooling process, then the piston is fixed somewhere here. The piston is not moving, okay? That's our assumption. So to have the piston not to move, moving upward, P, pressure by R134A plus minus atmospheric pressure minus PATM minus Fs, spring force. How you determine spring force? F is Kx, K is a spring constant, times X is distance. And the weight of the piston minus mg. And if the piston does not move, it means that the sum of this thing should be 0. Is this right or wrong? We have 2 minutes. Is this right or wrong? Yeah, right. It's wrong. So what is wrong here? Come again? No, that's not the right answer. What good guess? What is wrong here? Right, right. So this one is pressure. What is the unit? Pascal. This one is force. What is the unit? Newton. Pascal, Newton? No, you need to stick to one. So it's a force analysis. You can convert Pascal into force. How will you do that? F is pressure times area. So you need to multiply by the cross-sectional area of the piston. Then this one is correct. Then let's talk about this pressure, because we want to know what this pressure is, how this pressure changes. So the pressure of our system is going to be PATM plus K over A times X plus mg. So if you look at this equation, what do you see? Pressure, atmospheric pressure, is it variable or constant? Constant. Spring constant, variable or constant? A silly question, right? The name is a spring constant, so it should be constant, right? What about area? Constant. What about mass? Constant. Gravity? Constant. What about this X? That's the displacement of this piston. So it's variable. So pressure should be constant times X plus constant. So when you see pressure is constant times another constant times X. So what kind of, the graph is that? It's a curve, the linear. So you have a linear line here. Then what is the initial pressure? 600. What is the final pressure? Our system was here. So the pressure is 77.04. So initial pressure, 600. Final pressure, 77.04. And what is the initial volume? 0.3. What is the final volume? 0.1. So this is the final state. This is the initial state. We have a straight line. Can you determine this area? Yes, you can. Do you know how to, to calculate this area, right? This one plus this one divide by 2 times this one, right? So that's how you determine WB. So if you do, the area is going to be 67.704. So if you do this one, 67.704. However, as you can see, that was the initial state. This is the final state. So it is compressing. When you have a compression, moving boundary work is a negative value. So you have to say minus 67.704. Then you have everything but Q out. Now you can determine Q out, which is 1879.705 kilojoule. So that's how you solve this problem. Any question? Please review this problem after this class and make sure that you have a complete understanding and we don't have to review Thermodynamics 1 for closed system anymore. And next Tuesday, we are going to solve another, the problem for an open system, which will be also a little complicated like that. But if you can, practice these problems many times just to make sure that you have no difficulty, then we are good to go to start the interesting Thermo 2. Okay, thank you.